Hi, my name's Adi Chaudhary, APSC 171 T1A6 team lead. Did you know that in Canada, there are approximately 8,000 forest fires that happen every year, like the one behind me? Burning over 2.1 million hectares of forest? That's a lot of fire. Being the amazing 169 students we are, we performed extensive ideation, coming up with ideas such as foam-based fire retardants, GPS-based heat sensors, and heat-sensing drones. However, instead of focusing on fire prevention, we instead pivoted to the aftermath of the fire, namely these 2.1 million hectares of forest burnt and all those lost trees.
Currently, a lot of tree planting is done by volunteers who spend long hours out here doing labor, and that's backbreaking work. So the way we see it, there's a pretty clear need statement: a quick, efficient, and cost-effective way to plant trees in areas burnt by forest fire. And like the true future military industrial complex engineers we are, we designed a turret called TREES, which stands for Thermal Rocket Ecological Enhancement System. We identified 3 subsystems we would need to test via prototyping to ensure the feasibility of our product. 1, an aiming and control system. 2, a combustion-based launch system. And 3, the aerodynamics of our projectiles.
The first step in designing a tree turret is figuring out how to aim it. After all, I don't think anyone wants a tree ending up in their front lawn. So, after a little bit of time designing with pen and paper, I came up with the following 3-part design. First, there's the base. This houses the first motor and all the internals. Next up is this pan table, which, as well as tilting side to side, houses the second motor. And lastly, there's this tilt arm. That's connected to the second motor and controls the direction of the barrel. So, after modeling it all in SolidWorks, it was time to print. I think we ended up with a pretty cute looking turret. For control, we have these 2 potentiometers. Originally, we had a bang-bang control system, but after we talked to doctors Shirazi and Shaban, we made our code a little bit more adept and ended up with some relatively fine control. But this little guy is kind of small, and I don't think we could fit any real trees in there. So how about I pass it over to the propulsion team?
Say hello to my little friend. And myself, Adeo Kodra, head of the propulsionary team.
And I'm Stefan Cvetic, team secretary.
The tree system works via a combustion-based propulsionary system. Thus, to test this, we designed the material ordnance ejector, otherwise known as the MO. Now, the MO may look like a simple piece of PVC, but it's actually a highly engineered piece of technology.
So, how the MO works is first, the lid here is unscrewed and propellant is inserted into the combustion chamber. We've determined that the best propellant is propane. After the propane is inserted, we insert the seed pod rocket for universal tree planting into the barrel. You'll hear more about the sprouts later. Once that is done, the sprout is pushed down to the stoppers.
Stefan, let's stop talking about all this. Why don't we show the folks at home instead?
Good idea, Deo. Let's cut to that clip now.
Mo in 3, 2, 1. Whoa. 2, 1.
Wow, Adeo, that was fast, but just how fast exactly?
That's a good question. According to the calculations we performed earlier, we were able to determine that the maximum exit velocity of the sprout from the barrel was approximately 144 meters per second. We were able to determine this due to the camera's frame rate and the distance between the colored strips of paper. Thanks to our knowledge of APSC 181, we were also able to determine that the maximum theoretical distance that the MO is able to reach is approximately 80.5 meters.
Wow, Adeo, that's amazing. Now, let's fire it over to Mark and Antoine in the Sprout Projectiles department.
Whoa, what is this? What appears at first glance to be a simple plastic shape is the culmination of extensive aerodynamic analysis and design optimization, aimed at achieving the perfect balance between stability in flight and maximum range. Using SolidWorks, we conducted numerous fluid dynamic simulations to optimize the aerodynamics of our Sprout projectile. By modeling the airflow around the shell, we were able to tweak its design to minimize friction. This was crucial in ensuring that our projectile would fly reliably and fire reliably during flight. With this control, we can be confident that the projectile will land where we aim to maximize the positive impact on the environment and terrain.
Bei der Landung ist unser Projektil so konzipiert, dass es die Chancen der Seimenkammung maximiert. Alles beginnt mit der Hülle, gefertigt aus PLA, einem Material, das für seine biologische Abbaubarkeit bekannt ist. Diese fruchtbare Erde ist ein weiterer Schlüssel zu einer erfolgreichen Keimung, die den Samen in seiner optimalen Pflanzentiefe nährt. Während für diesen Samen eine Tiefe von 2 mm für die Keimung ausreicht, ist unsere Hülle tief genug, um jeden Baum zu Samen zu fassen und sicherzustellen, dass sie genau richtig gepflanzt werden. Im Boden wird die PLA-Hülle zerfallen und das Wachstum der Baumwurzeln ermöglichen, ohne eine Spur zu hinterlassen, außer einem gedeihenden Sämling. Hier in Sprout Labs pflanzen wir nicht nur Bäume, wir sichern ihr Überleben und ihren Wohlstand für eine grünere Zukunft.
Nice job, team. We're almost to the end of our video here, so we just have some closing notes on our idea. Our system is completely modular, meaning it can be attached to anything, especially to trucks like those used commonly in forestry. This is extremely beneficial as these trucks can navigate forest tracks yet still be able to access hard-to-reach areas that need reforestation. Our system will be able to fire a lot of trees per day, allowing for maximum efficiency. That's all for now. I gotta get back to planting these trees. Catch you cousins later.